Hello everybody, today I will tell you about electroactive hydrogel preparation, characterization and investigation of drug release potential by electrical stimulation. Pemetrexate, the sodium 2,5-hydrate compound, is a drug active ingredient used in the treatment of pleural mesothelioma and non-small cell lung cancer. In this project, I released the pemetrexate active ingredient to the hydrogel. The aim of this research is to reduce many side effects in patients, unlike traditional methods. Conductive polymers. We call a class of polymeric materials that can conduct electricity conductive polymers. These materials show thermal, oxidative stability, and optical properties. Sending a therapeutic drug to the organism that will prevent it from becoming sick or cure the disease it has its called drug delivery. It provides advantages such as accurate dosage, fast action, and wide usability. Here are some traditional drug release routes. Drug delivery systems can be examined under two different headings. One of them traditional drug delivery system and other one is new drug delivery system. What are controlled drug release systems? Controlled drug release is a type of new drug delivery system, sending the active substance directly to the pathological area and delivering the correct concentration to that pathological area is called controlled drug release. It reduces the negative effects caused by the disadvantages of traditional drug delivery. Controlled drug release systems are examined in three different classes. One of them is chemically controlled systems and the others diffusion control systems and solvent controlled systems. These are some of the advantages of controlled release systems. For example, better patient compliance, increased stability of the drug, reduced side effects of the drug, so on. The therapeutic window is a concentration time graph that shows at which interval the drug is the most effective treatment dose. Every drug has a therapeutic window. If the concentration of the active substance taken into the body remains below the minimum value, the therapeutic feature of the drug disappears. For this reason, it makes it necessary to take it with constant and frequent repetitions in order to keep the drug level in the body at the optimum level. Hydrogels. Hydrogels are widely used in the development of controlled drug release systems. They are polymers with a water holding capacity and cross-linked structure due to cohesion forces such as chemical bonds. They are insoluble water. It has very common applications areas such as industry, cosmetics, bioengineering, most importantly medicine. Smart hydrogels. One of the main subtitles of hydrogels is smart hydrogels. Smart hydrogels are also called stimuli-sensitive hydrogels. As seen in the figure, it exhibits swelling or shrinking behavior in response to external stimuli such as pH, temperature, electric and magnetic fields. The changes that occur are reversible. If the stimuli are interrupted, they have the ability to return their original state. Electrosensitive hydrogel is one of the best examples of smart hydrogels. First phase of the experimental part of the project, synthesis of non-electroactive hydrogels. Non-electroactive hydrogel production was attempted with the components polyethylene glycol diacrylate, 2-hydroxyethyl acrylate, ethylene glycol dimetacrylate in different ratios. Percent gelling, homogeneity, and mechanical strength tests were performed. According to the results, it was decided that the most suitable formulation was F4. Next step, preparation of the electroactive hydrogels. After deciding on the most suitable hydrogel formulation, 4 electroactive hydrogel formulations containing different percentages of pyrrole in the total formulation were prepared. It was decided to use the formulation containing 7.5% pyrrole. This measurement was made to examine the conductivity of pyrrole-containing hydrogels. In the measurements, hydrogels containing different amounts of pyrrole were coded with different names and measured. It was observed that the conductivity of the hydrogel reached its maximum level with 7.5% pyrrole, and there was no increase in conductivity as this pyrrole percentage increased. As a result of these measurements, it was concluded that the percentage of pyrrole with the largest and most stable voltammogram graph was 7.5% pyrrole. Swelling studies. As a result of the calculations, it was calculated that both hydrogel types exhibited similar behavior and swelled by an average of 15.4%. FTIR analysis. In order to confirm whether the electroactive hydrogel contained pyrrole, FTIR analysis of both electroactive and non-electroactive hydrogels was performed. Thermogravimetric analysis. As a result of this analysis, it was concluded that the thermal resistance of the electroactive hydrogel was higher. The fact that the mass loss of the electroactive hydrogel is higher than that of the non-electroactive hydrogel confirms this trend. The temperature at which the main loss occurs is given in the table for both hydrogels. Scanning electron microscopy. The swelling behavior of hydrogels is directly related to the surface area properties of hydrogels. As the surface roughness increases, the contact of the molecules that cause more swelling to the surface also increases. As can be seen from the SEM images of these two different types of hydrogels, there are no pores on either surface as expected. Scanning electron microscopy results also support that both hydrogels show near percent swelling on average. Preparation of pemetrexate loaded electroactive hydrogel. Pemetrexate loading was performed by immersing the 3-electrode system in the reaction cell containing 4 ml of 0.01 millimolar pemetrexate solution and applying a potential of 0.6 volts using the chronoamperometric method for 30 minutes. In vitro pemetrexate release profile. At this stage, the release of pemetrexate from PEM-loaded electroactive hydrogels into phosphate-buffered saline in the presence of electrical stimuli was investigated by UV visible spectroscopy for a period of 33 minutes. Absorbance values at 225 nanometers were used in the calculations. It was concluded that the amount of the drug release from electrically stimulated hydrogels was higher than that of passive control samples, and the amount of drug release increased as the release time increased. I would like to thank my esteemed teacher, Associate Professor Melike Fırlak Demirkan, and I would also like to thank TÜBİTAK for their financial contributions. Thanks for your listening and attention.